This problem is a slightly modified version of 4.91 from your text. It is an example of a redox titration. If you haven't already read the problem, pause this video and take the time to read it carefully. Okay, so in this problem we have a reaction, a redox reaction, between dichromate and iron 2+. It says that iron 2 can be oxidized by the potassium dichromate solution, and they give us the net ionic equation for the reaction. And if you look at that reaction carefully, you see that you have dichromate anion, Cr2O7 2-, plus iron 2+, and the iron 2+ is oxidized to iron 3, and the dichromate is reduced to chromium 3+. The question says that it takes 26 milliliters of 0.25 molar potassium dichromate solution to titrate 25 milliliters of a solution containing iron 2+, and they want you to determine the concentration of the iron 2+ solution. So while this seems complex, it's really no different than doing an acid-base titration, for instance, and just simply builds upon the previous stoichiometry problems that you've already done. So at the heart of this is really just a stoichiometry problem. The difference is that we're starting with solutions instead of mass quantities of our reactants. To help myself out, I like to make a drawing of the titration setup itself. So I'm going to draw a burette here, and this burette will fill with the potassium dichromate solution, which is yellow, nice intense yellow. Let's fill that in. I'm going to label this potassium dichromate and write the concentration 0.250 molar to remind myself. So we have that in the burette, and that's going to be titrated into iron. So let's write a rough drawing of a flask here. We're going to fill it with iron solution, which I'll color in a kind of a pale bluish green. And let's label that also. We have 25 milliliters of this solution of iron 2+, and I'm putting concentration question mark because the question asks what is the concentration of iron 2+, so we should write that down explicitly. As you titrate in the 26 milliliters, okay, we'll find that the reaction will be noted by a change in color. So we're titrating in a certain amount of potassium dichromate, and because the dichromate is an intense yellow and the iron is only a pale color, the iron 2+ is pale, chromium 3+ is a pale green, and iron 3+ is light yellow. So there's a lot of color here, but the dichromate is so intense that it's going to overwhelm everything. And so what will happen is as you're titrating in the dichromate, you would see a intense yellow as it hit the solution, which would then be rapidly consumed by the iron 2+, being oxidized to iron 3+. However, once you reach the equivalence point, once you have just enough dichromate to react completely with the iron 2+ in the flask, you've reached the end of the titration. One drop more, and there'll be just a little bit excess dichromate, and the solution in the flask will turn a darker yellow color. That will indicate that we've reached the end point, hopefully as close to our equivalence point as possible, and the end of the titration. So end of titration, we have a slight yellow, and now we're ready to make a plan about how we're going to solve this. Okay, so let's think about this. At the heart of every stoichiometry problem is the chemical equation. And we know that for every 1 mole of dichromate we add, it's going to react with 6 moles of iron 2+ that's in the flask. So we have a direct relation between the amount of dichromate that is used in the reaction and the amount of iron 2+ that's reacted. And we can use this information to our advantage. Now, they've given us the information about the dichromate. We know the concentration and the volume. And from the concentration and the volume, we should be able to determine the moles of potassium dichromate. And from the moles of potassium dichromate, we can of course get the moles of the dichromate anion. It's simply 1 to 1. And that's perfect because, as you can see, that brings us to our balanced chemical equation, which shows 1 mole of dichromate will react with 6 moles of iron. And so from this, I can determine in our 1 to 6 ratio the moles of iron that were in the flask. And of course, we know exactly what volume we had in the flask to begin with, and the moles of iron divided by the total volume of iron solution will give us the concentration in moles per liter. So this is our plan. We're going to first determine the moles of potassium dichromate, the number of moles of potassium dichromate it took to reach the equivalence point, and that's based on the volume that was delivered from the burette and the concentration of the potassium dichromate. And then we'll use that to determine moles of iron that was in the flask from our balanced chemical reaction, and then the moles of iron and the volume of the solution will give us the concentration of iron in the flask. Let's go ahead and execute this plan then. I'm going to put a little border here too, so it's a little more separated. Okay. Moles potassium dichromate is equal to 0.250 moles per liter times 0.0260 liter. Notice that I've converted, I didn't actually show the calculation, but we've converted the 26 milliliters to liters. So 26 divided by 1,000 converts it to 0.0260 liters. And I've written out the molarity in moles per liter. So I can explicitly show how the units cancel. Liters cancels, leaving us with 0.00650 moles of potassium dichromate. The moles of the dichromate anion then are simply equal to the moles of potassium dichromate, so we have 0.00650 moles of dichromate ion in solution. Perfect. So now we can calculate the amount of iron that must have reacted with in the flask, the moles of iron. We can calculate 0.0065 moles of the dichromate anion times we have a 6 mole iron 2 plus to 1 mole dichromate ratio. And that results in 0.0390 moles of iron 2 plus. So that is the amount of iron 2 plus that must have been in the flask in that 25 mils. So in the last step, to get the concentration of iron 2 plus in moles per liter, we simply take that number 0.0390 moles of iron 2 plus divided by the volume that was in the flask, 0.025 liters. Notice that I've again converted that original 25 milliliters that was provided to us to liters, so we have the correct unit, and that equals 1.56 moles per liter iron 2 plus. Notice again, just to reiterate, that the heart of this problem is really a stoichiometry problem. The difference is that we are using volumes and concentrations to determine the number of moles of the reactants involved in the reaction. But otherwise, it's pretty much like a normal stoichiometry problem.